We're unraveling a pretty gripping mystery today, right at the cutting edge of AI and drug discovery. Just imagine for a second that you're running a massive pharmaceutical pipeline. You're relying on this highly trusted, mathematically backed AI method to act as your ultimate gatekeeper. Its entire job? To tell your team exactly which chemical compounds are safe and promising enough to synthesize and actually test in a physical multi-million-dollar wet lab. Now, this machine learning method promises you a rock-solid safety net. And on paper, in the aggregate, it looks absolutely flawless. It gives your team incredible confidence to move forward, but behind the scenes, hidden right beneath those reassuringly high aggregate metrics, there is a quiet failure happening. The system is secretly abandoning the most critical data, leaving rare, but absolutely crucial, chemical labels dangerously exposed to error.
Okay, let's dive into this. 90%. In the world of conformal virtual screening, that's the golden number. It's this global coverage target that makes standard, or what we call marginal, conformal prediction look incredibly reliable. Look, when drug discovery teams deploy these ranking models, they desperately need to know they can trust the output before they commit real physical resources to synthesis or an assay. And the beauty of marginal conformal prediction is that it looks at the entire data set as just one giant bucket. With a 90% global target, the math practically guarantees that if you draw a prediction, the true label of a compound is going to be captured 9 times out of 10 overall. For anyone managing a lab budget, well, that looks like a massive, reliable win for AI-driven chemistry.
But here's the devastating paradox. When researchers audited this exact same method on critical, highly imbalanced datasets, like clinical trial toxicity data, for instance, the realized coverage for the minority class just plummeted. I mean, it didn't just dip, it completely collapsed to a disastrous 4.2%. Think about what that practically means for a second. If you were looking specifically at these rare, highly toxic compounds, you'd literally have better odds picking compounds out of a hat blindfolded than relying on the model's calibration. For the rare, often most critical chemical cases, the algorithm is entirely abandoning its promises. So that raises a massive question, right? How exactly can an AI model confidently claim 90% global accuracy while completely dropping the ball on the rare data?
Section 1. Unmasking the coverage gap, when 90% isn't what it seems.
To really understand how that massive coverage gap happens, we need to clarify what conformal prediction actually does in the first place. It's a statistical method that's gaining massive traction precisely because of its calibration guarantees. In plain English, you pick an error rate, let's just call it alpha, and the method returns a prediction set containing the true label with a guaranteed probability of at least 1 minus alpha. Think of it kind of like a weather forecast. Instead of an AI just guessing tomorrow will be exactly 72 degrees, conformal prediction gives you a temperature range, say 68 to 76 degrees, and mathematically guarantees the real temperature will fall inside that range 90% of the time. It offers this amazing theoretical promise of putting an honest, mathematically sound number on model reliability. But, as we're about to see, when your dataset isn't perfectly balanced, that guarantee becomes incredibly dangerous.
Just look at the sheer scale of the drop-off across these 3 highly imbalanced drug discovery datasets. The biological gravity here is immense. First up, we've got blood-brain barrier penetration, which measures whether a drug can safely cross into the brain. Here, the minority coverage drops from that target 90% all the way down to 64.8%. Then we have the TOX21 toxicity endpoint, which is essentially detecting whether a compound will act as a poison to human cells. The coverage falls to 38.9%. And then the absolute floor, 4.2% on clinical trial toxicity. But the global aggregate accuracy across the whole dataset, it stays reassuringly high at 90%, completely masking these specific drops. That's exactly why this mathematical bug is so incredibly easy to miss if you aren't looking really closely at the rare classes.
Now, you might naturally assume, hey, this is probably just a single bad model hallucinating, right? Actually, scratch that. Research confirms this failure is structural. It's not architectural. It reproduces across highly diverse setups. Seriously, it doesn't matter if you're using random forests on circular fingerprints, graph convolutional networks that read the molecular structure directly, or even frozen pre-trained chemical language models. They all reproduce this massive undercoverage on rare labels. Why? Because the underlying statistical net catching the answers is what's full of holes. The math itself is flawed regardless of the fancy AI architecture you place on top of it. This undercoverage tracks strictly with the baseline calibration on rare labels, definitely not the specific architecture you choose to deploy.
Section 2. Why the math fails. The conservation identity.
This quote right here from the research is the key to the whole mystery. The minority class coverage shortfall equals the majority class coverage surplus. This is known as the conservation identity, and it perfectly explains the mechanics of the failure. Essentially, marginal conformal prediction acts like a reverse Robin Hood. The math literally steals accuracy from the poor, the rare minority classes, to pad the stats of the rich, the massive majority classes. Because the algorithm is just trying to hit that 90% global average, it takes an optimization shortcut. Computationally speaking, it's just much cheaper and easier for the model to be 95% right on the massive majority class, completely fail at 0% on the tiny minority class, and still average out to 90% overall. This identity is so mathematically precise, it actually predicts the measured coverage gap to within one single percentage point. Crazy, right?
So, what does this all mean? And more importantly, how do we fix it? Well, we move from marginal conformal prediction over to class conditional conformal prediction, which is often called Mondrian conformal prediction. The name is actually a fun reference to the artist Piet Mondrian. You know, the guy famous for those paintings that partition canvases into distinct rigid squares. Well, just like the artist, this method partitions the data space. Instead of looking at the global average and letting the majority class bleed over and steal from the minority, the Mondrian method acts as a firewall. It computes conformal sets entirely independently for each specific class. By enforcing the coverage guarantee strictly within each partition, it completely stops the majority class from cannibalizing the minority. Problem solved.
Section 3. Real-world drug discovery costs. The price of false negatives. Okay, let's ground this abstract math in the physical reality of $1 million wet lab. In virtual screening, teams use these ranking models to prioritize compounds for real-world testing. When standard prediction delivers high global accuracy, teams trust it, and they move straight to synthesis. But the researchers found that the failure localizes on generic molecular scaffolds, specifically plain benzene and pyridine cores. These are foundational, ubiquitous building blocks in organic chemistry. Because they're so incredibly common, they show up frequently in both the majority and the minority classes. This makes it virtually impossible to just filter them out using basic structural rules. And because of the mathematical bug, teams are unknowingly throwing away vital, perfectly viable compounds built on these cores, entirely due to false negatives that the math confidently told them were correct. Which brings us to a really remarkable cost model analysis from the study. If a lab continues to deploy standard marginal methods, they are practically guaranteeing wasted physical assay resources and missed therapeutic leads. However, if they change up their approach and choose to abstain on these specific affected compounds, meaning instead of automatically tossing them in the trash, they raise a flag and route them to human experts or maybe run a secondary computational check, it completely changes the return on investment. Simply catching this mathematical bug and routing the edge cases literally flips a screening campaign from net negative to net positive utility. It's a real game changer.
Section 4. The class conditional fix. Restoring per-class reliability. So what's the actionable protocol here? The researchers lay out this exact 4-step workflow for developers to implement right now. Step 1. Calculate your per-class coverage metrics during calibration. You have to use the minority coverage gap as a core diagnostic during any model update to actually see if you have a problem in the first place. Step 2. Apply those Mondrian scores we talked about. Partition your calibration data by label and compute the sets independently to build that firewall between classes. Step 3. Configure your screening pipeline to abstain on high-risk scaffolds. If coverage drops below your target for those common benzene or pyridine cores, whatever you do, do not auto-discard them. Route them to manual review. And finally, step 4, monitor prediction set size inflation. You just need to keep a close eye on how the model is adjusting its confidence intervals.
Naturally, as a practitioner, you're probably wondering, okay, what's the catch? Well, the trade-off for using this class-conditional Mondrian method is a modest increase in the average size of your prediction sets. The model might hand you a slightly wider range of possibilities to guarantee that 90% accuracy on the rare classes. But look, in the grand scheme of a pharmaceutical pipeline, this slight computational overhead is completely negligible. You're basically paying pennies for modern GPU compute to achieve a massive reduction in false negatives during downstream physical validation. When you benchmark a tiny computational cost against the exorbitant budget of synthesizing dead-end chemical compounds in a physical lab, yeah, it's a trade-off worth making every single time, for sure.
Which brings us to a vital question that every single team working in machine learning for drug discovery needs to ask themselves right now. Is your 90% global coverage masking a quiet failure? If you're still relying on standard marginal conformal prediction without checking your rare classes, the odds are dangerously high that it is. But the good news? The fix is mathematically proven and readily available. It is absolutely time to audit your machine learning pipelines, calculate your per-class metrics, and make absolutely sure you aren't unknowingly sacrificing your most critical discoveries just to maintain a reassuring but totally deceptive global average. Go check your pipelines today. Thank you so much for joining me on this explainer, and happy screening.